we're going to look at question 38. Now, this is another inverse question, and this again is on page 417, but this one varies inversely to the square. So all we have to do is square. So let's look at question 38. And these are not bad to set up at all. They're much simpler than most of the applications that we've done. All you have to do is set up the formula, plug it in, plug the values in. So question 38. The illumination produced by a source light varies inversely, so that means we've got a fraction, so very important with the wording here, inversely as the square of the diameter of the source. You can label these however you would like. We know that it's inverse variation, so that means it's going to be a fraction. And it's squared, so inversely squared. So inverse means a fraction. And this is going to be inversely to the square. So we're going to look at however you want to label them. Let's call it illumination, because that's our first thing. However you want to do it, you could say light, whatever you want. And it varies inversely, so that means we've got a fraction. Now, k always stays the same. K is our constant on the top. And it says it varies inversely, so that means we've got a fraction. Inversely, though, but to the square of the distance. So that's going to be the distance squared down below. So that's our only difference. Is instead of it just being inversely, now it's inversely to the square. If it would have been inversely to the cube, then this would be a 3 power. But it will tell you how to write it. If it says square, it's 2. If it says cube, it's 3. It could be a square root. If it was a square root, you just put the square root down. Now, we fill in what we know. And what do we know here to get our constant k? It says inverse is the square of the distance. The illumination of a source at 5 meters is 70 candelas. So 70 is going to be our illumination. That's in candelas. K is again unknown. And what's our source distance? Our source distance here is 25, isn't it? Nope, 5. Sorry about that. Illumination of the light source at 5 meters. So we want 5. And we're going to have to square that. So that's going to give us our 25. So now we know when we plug our values in that we have 70 equals k over 25. And all we have to do is cross multiply. And that gives us now, when we cross multiply, now we had to square it, that 5 to get to 25. 70 times your 25, well, that comes out to then be 1750, and that's your k. So we just simply cross multiplied there. And that gave us our value of k. Now, once we know our value of k, then we can rewrite it. So your illumination is now going to equal 1750 over the distance squared. There's our new formula. So all we're doing is just writing up the formula. And light spreads out so fast, that's why when you increase that distance, it goes by the square. So you decrease your illumination by the square of that distance, because a little change in the distance makes a big change in the brightness of the light source. Okay, now what do they tell us to plug in for our values? We want to find the illumination when it is 12 meters from the source. So that means my distance now is going to be 12. So the illumination is going to equal 1750 over 12 squared. And so that is then 1750 over 144, because 12 squared is 144. And we can reduce that down. And we want to keep it as a fraction. So we'll just reduce that down. Let's see here. Can we put a 12 through there? No. Can we put an 8 through there? Nope. So we've got 144. We can divide that by 4. We've got 1750. We can divide that by 4. Won't go in there. How about a 6? Nope. Let's see. So I think we can reduce that down just a little bit here. I know at least a 2. So we can reduce that down by 72. And 1750, we can reduce that down by a 2, and that's 875. Okay? And all we did is we reduced it. And you could use a decimal. I prefer you keep it as a fraction, though. But if you did a decimal, it'd be okay as well. And that's going to be candelas. And we just kept it as a fraction. And I just tried to reduce it as much as I could, and I could only reduce it by a factor of 2. Okay. Now we're going to talk about joint. And in joint variation, several things can go together. Now, when we talk about joint variation, anytime you have several things going together, if it says inverse, that means divide. If it doesn't, that means we just keep it on the top. So we're now going to look at a couple of these, and these are joint variation. And joint just means we have multiple variables or multiple things going together. So when we talk about joint variation, that just means you have multiple variables. So several things go together to influence another variable. And we'll look at question 40. Now, what does it talk about when we say directly? Directly means we multiply. Inverse means we divide. That's all we have to remember. Direct, multiply, inverse, divide. So we're looking at the volume of a gas in a container. So the volume of the gas varies inversely as the pressure and directly to the temperature. And that makes sense because what happens with gas? Okay, if I've got gas, and let's think about the just anything. Okay, when I increase the pressure, what happens to something? Okay, if I take a soda can and I increase pressure on it, it gets smashed down, right? So as you increase the pressure, what happens to the volume of that gas? Volume of the gas goes down as well, right? Increase the pressure, gas volume goes down. What happens with the temperature? Okay, well, as you increase the temperature, it's directly, so it's going to make it get bigger. So that's two things going together to change the volume of this gas here. So now, first thing we look at is which one's listed first. It says the volume of the gas. So that's going to be our first one, volume. Inversely means we divide, so divide by the pressure. Directly means we multiply by the temperature. So what would that look like now? What do we start with? We start with the volume. So the volume of that gas. It says it varies inversely as the pressure. So we still have our K. K is always going to be there. You have to find the K every time. Inversely as the pressure. So that goes down below. Directly as the temperature. So there we go. There's our formula. Now we've got to find that value of K again. So if a certain gas occupies a volume of 1.3 liters, so that volume is 1.3, so we plug it in. K again is not known. At 300 degrees Kelvin, so that's your temperature. We'll do the 300 here. at a pressure of 18 newtons. We use pounds, but we're under the English system, the imperial system. If you use a standard system, you'd use newtons instead of pounds. And you'd use kelvins instead of Fahrenheit. But we use the empirical system, but you can use the standard system as well, the metric system. So now we just work with this. So let's see how we can work with it. We'll just go ahead and multiply. So easy enough. We'll just clear out the fractions by simply multiplying here. So we've got now 1.3 times that 18. That makes it 23.4. And that's going to be 300K. You've got decimals, and if they use decimals, just go ahead and use a decimal. So now we'll just divide this by 300. And we now have our value of K. So 23.4, we'll divide that by 300, and that comes out to be 0.078. And if they have decimals, just use decimals. If they have whole numbers, just keep the whole numbers. What's our formula now look like? Volume equals 0.078 times the temperature divided by the pressure. Now we need to find our new volume. So it says find the new volume. Temperature is 340 degrees Kelvin. Pressure is 24 newtons. So temp is, in this case, temperature is 340 degrees Kelvin. So that goes there. Pressure of 24 newtons. It's 24 there. So we've got the temperature and we've got the pressure recorded. We can find the volume of that gas now. So we just plug our values in, calculate it out, and we're done. So that's 0.078 times the temperature of 340 over a pressure of 24. And that gives us our new volume of the gas. 340, divide that by 24, so 0.078 times 340, and we'll divide that by our 24, and we get 1.105, and that's going to be in liters. So that's how much space that new gas would occupy. So they're not bad to set up. And the textbook has you use X and Y, but then you get mixed up as to what X and Y are. I think it's easier on these just to use words. That way we don't get confused with the formulas, because you start using X and Y, you'll inadvertently mix up the X and the Y, and it's way more confusing. Okay, let's look at another one here. How about 43? So the roof of a new sports arena rests on some concrete pillars. The maximum load a cylindrical column of a circular cross-section can hold varies directly, and this is important here, varies directly as the fourth power of the diameter and inversely as the square of the height. So we got to make sure that when we look at these, we know what goes where. And in this case, they're going to be raised to a power. So what are we looking for? The roof of a new sports arena rests on circular concrete pillars. The maximum load that it can handle varies directly. Okay, so what are we looking at here? We are looking at the load of this column can handle. So we'll just say that's going to be the maximum load on this column. So the maximum load that can handle is going to what? If you read it here, varies varies directly as the fourth power of the diameter. So directly means we multiply. Okay, and it says directly as the fourth power. So that means diameter has to be raised to the fourth power. Now the k is still out in front. And it says inversely as the square of the height. And let's take a moment to think about this. We're not physicists, but just think with some common sense here. The bigger the diameter of this column, the more it can support, right? The taller you make it, the less, because it's going to want to topple over and have to be made reinforced more. So when you increase the size around of that column, it can hold more, but as you increase the height, it holds less. So that's why one is directly, one is inversely. And they're not just directly, then they're directly to a power and inversely to a power. Now again, we still have to find that k. So what do we know here? The arena has a 9-meter tall columns that are 1 meter in diameter. So the height of these columns is 9. The diameter of these columns is 1. So the height of these columns is 9. Diameter is 1. And they support a load of 8 metric tons. So now we just plug our values in. So we have our load, which is 8 metric tons. K is unknown. Diameter is 1, but we've got to raise that 1 to the 4th power there. We're going to divide that by the height, which is 9. And we have to square it. Okay, so everything gets plugged in. Now we can work with it. So we've got 8 on the left, which stays the same. 1 to any power is just 1, so that's just going to stay as 1. We won't even write it. We'll use a k there, because 1 times k is just a k. And 9 squared is 81. Now we can go ahead and cross multiply here. And that gives us now, when we multiply, k equals that 8 times that 81. And that comes out to be 648. So that's our value of k. Now we're going to plug this back in, rewrite our formula. So what's our new formula look like? The load that those columns can support is going to be 648 times the diameter to the 4th power. Over the height squared. There's our new formula. Plug in our values. So what do we want to find? We want to find this load again. Okay, how many metric tons will be supported by a column that is 12 meters high and 2/3 of a meter in diameter? So there's our numbers. Now, what do we think is going to happen here with this? So what's happening to this column? Column got smaller. Okay, so when the column got smaller, what happened to the load that it can carry? Less. Column also got taller. Since the column got taller, what happened also to the load that it can support? Got less, because it's down below. So the load that this can handle is going to be substantially less, especially because you have to take that diameter to the 4th power. So let's go ahead and work with this. We're going to plug our values in, and then we'll just work with that fraction over to the side. We don't want to use a decimal because 2/3 goes on forever. And we'd have to round it. So we're just going to keep that fraction. So let's go ahead and work with this quickly here. Now, what about 2/3 when we take it to the 4th power? 2/3 to the 4th power would be 2 to the 4th over 3 to the 4th. And 2 to the 4th power is 16. 3 to the 4th power is 81. And down below, 12 squared is that 144. So let's see what we can do here. Now we need to go ahead and combine, and we don't really want to go to decimals unless we have to. We're going to keep it as a fraction as long as we can. So let's just go ahead and work this out a little bit neater here. 81 and 648, I don't think they have a 9 in it. Actually, it does. So we'll try to reduce this down. We've got 648 over 1 times 16 over 81. Okay, those have a 9 in them, so 648. Divide that by 9, that's going to be a 72. And a 9 down here. Does 72, does that have a 9 in it again? It does, right? So it leaves you with a 1 and an 8. And so we can just multiply directly across. And that gives you 128. So 128 over 144. So I just went through, and I could have saw that it had an 81 to begin with, but I didn't. So I just divided by 9, divided by 9 again. And I got to this point and should be able to reduce it down by at least 2. Let's try a 4. 4 will go in there. So that's 32. And 144 divided by 4, that's a 36. We can go a little bit more, I think, because 2 goes in there again. 2 and 16. 4 will go in there. Let's try a 4. So if I use a 4, that's going to be an 8. And 36 divided by 4 is a 9. And I think that's as far as I can go. So it looks like that is as far as I can go. And so what does that mean? That means that new column can only support 8/9 of a ton. And if you really struggle with the fractions, you can use a decimal. I'd prefer that you keep the fractions so that you don't have round off. But if you really struggle with the fractions, just use decimals. Or you can use a calculator that does fractions for you, either way. Okay, how about we look now at 46. And 46, we're looking at a car. And we're going to have to determine all the factors that are involved with the car wanting to skid around a curve. So the force needed to keep a car from skidding on a curve varies inversely as the radius of the curve and jointly as the weight of the car and square of the speed of that car. So what's going to make it more likely to skid around? Okay, the heavier the car, right? Heavier the car, less likely it's going to be want to skid. Because once you have a lot of weight, once it starts to skid, the heavier the car will skid more. But to make it skid, the weight varies with that. Okay, and what else? Speed, right? The faster you're going, the more likely it's going to be to skid around. What else makes it less likely to skid around a curve? Well, the radius, because the bigger the radius, right, the less of a curve you really have, and so the less likely you're going to be to skid around. So let's try to come up with our equation. In this case, we have three variables that influence one variable. So the force needed to keep a car from skidding. So we're going to say skidding. That's what we're looking at, is the skidding of a car. And what happens with the skidding of the car? Skidding of the car varies inversely as the radius of the curve. So inversely means it goes down below. Okay, so the radius is down below. Jointly as the weight of the car and the square of the speed. So jointly is just the same thing as directly. They go together. We don't know K. K is going to be our unknown. And what's going to go on the top is the weight of the car and square of the speed. So the speed has to be squared. So there's our new formula. Now again, filling in our values, we will find our K. So we went out and we measured. It takes a 3,000 pounds of force. So the skidding of that car, force it takes to keep the skidding away, is going to be 3,000 pounds. So 3,000 pounds of force is going to need to be used to keep a car that weighs 2,000 pounds. So the weight of that car is going to be your 2,000. Radius is 500, so radius is 500. And your speed of this car is 30. So plug in our values. So we've got 3,000 equals K, which is our unknown. The weight of that car is 2,000. Speed of that car is 30. We have to square it. Divided by the radius of that curve, which in this case is 500. So I'm going to go ahead and cross multiply and break it down. And this is just calculation, so you just use a calculator here. We've got our 3,000. Multiply that by that 500. And that's going to be, it looks like a 1.5 million or 150000 again. And that's going to equal K. And what's going to be multiplied by that K? Well, we've got 30 squared. Okay, so that's 900 times your 2,000. And that makes it 1,800,000. Make sure I got the correct number of zeros here. Yep. Okay. And now we just divide. I'm going to show you a shortcut here. When you divide, those zeros can cancel out. So these three zeros cancel. Those two zeros cancel. So now you're left with 15 over 18. And I believe I can reduce that down a little bit more because they both have a 3 in them. So that's going to reduce down to be 5/6 there. So whenever you have those zeros, they can all cancel out. So that's going to be our new K. Now we simply rewrite it. And let's rewrite our formula. The force needed to keep a car from skidding around a curve is going to equal 5/6 times the weight of the car times the speed squared of the car divided by the radius. Now we need to find out the weight, the force to keep the car from skidding here. And it says, what force will keep the same car from skidding on a curve that has a radius of 800 feet at 60 miles an hour? So we're going to use the same weight. So the same weight of the car. Okay, and the weight of that car is still 2,000. So the weight didn't change. Weight stays at 2,000 pounds. But we did change some variables in here. We changed that radius of that curve to be 800 instead of 5. And we also changed that speed to be 60. Now the force that we need to keep this car from skidding, and that force is the tires control the force there, the stickiness of the tires and the rubber. It's going to change quite a bit. Why? Because what's squared here? The speed is squared. We doubled the speed. Okay, when you double the speed, because the speed up here was 30, right? When we square it, we more than double it. When you square something, if you double that speed, 2 squared is 4. So it actually increases it by 4 times. So the force that's going to be needed to keep this car from skidding is going to be dramatically more because that speed went up and that speed is squared. Squared, when you square 2, right, you double it, so you square it. 2 squared is 4. So it's 4 times as much. Now the radius went up some. And when the radius goes up, that decreases the force, but not nearly as much as the speed because the speed is squared. So now we can just plug our values in. And we have 5/6 times the weight, which is your 2,000, times the 60 squared. And that's all going to be over 800. And that's going to be the force needed to keep the car from skidding. Okay, so let's just go ahead and work this out. And I'll just do the numerator over here. And 60 squared is 3,600. And we'll just do some cross multiplying here. So that 3,600, that 6 can go in there. And that's going to leave you the 1 and a 600 here. And so now we'll just multiply across. So we've got 5 times 2,000 times your 600. Okay, make sure we get the right numbers here. So that's 6 million. We're going to divide that by 800. So those can cancel. 2 zeros cancel out. So that's then 60,000 it looks like. Yep, because those 2 zeros are gone. Over 8. And 60,000 then divided by 8. And again, you could just use a calculator here. I'm just doing most of it by hand. But that's 60,000. Divide that by 8. That gives us then 7,500 pounds of force. So we really increased the force that we needed to keep that car from skidding. Before it was only 3,000. Now we've got to make sure that the car can do 7,500 pounds. And that just relates to how sticky the tires are. So you'd have to change the tires to keep the car on the road. Do what now?
Nothing. She just looked at me and I was like, oh God.
But see, they're not hard to do. And if you want to, you can just use a calculator and run through all the numbers. The hardest part is just plugging the values in and using a calculator. Once you get them set up, they're easy. Let's do one more and then we'll take a break. Let's look here at question 50. And they're actually kind of neat to see how things relate to each other. So question 50. And this will be the last one that we're going to look at. So we'll take a break after this, come back, and we'll look at a different topic. So question 50, we're looking at the detonation of a nuclear bomb. So suppose the effects of detonating a nuclear bomb will be felt over the distance from the point of detonation that is directly proportional, that means we multiply, to the cube root of the yield of the bomb. Suppose that a 100 kiloton bomb has certain effects to the radius of 3 kilometers away from the point of detonation. We want to find the nearest tenth, the distance for which the effects will be felt for a 1500 kiloton bomb. So, how do these relate? This is not a joint one anymore. This is varying what? Directly. And what does it vary directly to? It varies directly to the cube root. So, suppose the effects of detonating a nuclear bomb will be felt over the distance from the point of detonation that is directly proportional to the cube root of the bomb. So we've got the distance that we can feel it. That is going to be directly proportional to the cube root of the yield of the bomb. So K is our constant again, and we're looking at a cube root of, we'll just say the bomb size here. So it spreads out in a circle, right? So it's not just directly, it's directly to the cube root. So the bigger the bomb, the more you're going to feel it, but it's got to be a huge bomb to make it much of a difference at all. Just like an earthquake. You know, it's really, really powerful at the center, but as you go out from the earthquake, you don't feel it near as much. So it won't take us long to go through this one. We've got the bomb that's 100 kilotons, and it gives us a radius of 3. So our distance that we can feel it is 3, and the bomb is going to be 100. So the distance is 3, and that's K, and we want the cube root of that 100. Now, 100 is not a perfect cube, I don't believe. Right? So 100 is not a perfect cube, so we're just going to use our calculator. And it doesn't say how far to round. Oh, it does. It says, yep, find it to the nearest tenth. So we're going to take this out, let's say, just so we get a good value for K. We want tenths, so we're going to add 2 more places. So we're going to take this out 3 places to find the value of K. How would I plug in the cube root of 100 into the calculator? Well, there's different ways of doing it in the calculator. You can take it to the 1/3 power, which is the same, or you can use the cube root button. If I use the 1/3 power, here's how you type it in: 100. Use the caret key, parentheses key, 1, divide key, 3, close parentheses key, and then hit the equals key. So you can always transform those roots to a fractional power. Same thing as if you wanted to do the square root. You could use a half power. We have a square root key in our calculators built in, but if we didn't, we could do it with a half. So a cube root, we take it to the 1/3 power, and then we're going to write this out to 3 places. So I'll put it up so you can see it up on the screen. So 100, we hit the caret key, parentheses key, 1, divide key, 3, close parentheses key, equals. And we're going to round this out to 3 places. So that's 4.64 if we round 2. That's our value of K. Well, not K yet, but that's the value of the cube root of that 100. divide by that 4.642. Now we've got our value of k. And when we divide that out, that gives us a k of 0.646 if we round. So that's our value of k. Now we wanted 3 places because we're going to round to 1 at the end, so we'll do a couple of extra so we can round to the nearest tenth and get it right. So now rewriting, the distance is going to equal 0.646 times the cube root of the size of the bomb, right? Okay, now what are we doing? We are changing this bomb, and it was 100 kilotons. Now it's 150 kilotons. Or not 150, 1,500. Sorry about that. So that bomb is going to be 1,500. You might think it's going to make a much larger distance that we can feel the bomb on, but it's really not because it's a cube root. So it will make it bigger, the distance going out, but not as much as you think. Just like earthquakes, bombs go out in a circle like this. And so it's really expanding out. So it takes a lot of energy to make it really expand out a lot further. Just like an earthquake. You have to have a really, really powerful earthquake to feel it a long distance away. So let's go ahead and plug this in. So our distance, we don't know. We want to find that. And that's going to be 0.646 times the cube root of that 1,500 pound or kiloton bomb. And how do we do the cube root of that 1,500? Well, that's going to be 1,500. We hit our caret key, parentheses key, 1, divide key, 3, close parentheses key, and our equals key. And what does that come out to give you? That comes out to be 11.44 if we round 7. So 11.4, so it looks right here, 11.447. And we're going to have to multiply that by the 0.646. So that gives us then, if we round the nearest tenth, 7.4, and that's going to be kilometers. So we way more than doubled the strength of that bomb, but we really didn't change so much how far away it can be felt. So it really takes a really, really powerful bomb to make much of a difference in how far away it is for you to feel it. So let's take a short break. We're going to come back. And then we're going to start looking at, I believe the next topic is logarithms and exponentials.